Hi again, this is the base knowledge for short circuit calculation, the impedance equivalence circuit preparation. We are done with the base knowledge 3, 4, 5 on short circuit. Let's proceed to number 6. I hope you are now very eager to start it because this module is very different as you can see. One by one, I open to you the step in base knowledge so that I will let no void question in your mind related to short circuit calculation. Now I will discuss the preparation for the impedance diagram, the most tedious work in short circuit calculation. The two base knowledge I will discuss are creating impedance circuit or impedance equivalent diagram and basic Ohm's law formula for short circuit calculation because the two base knowledge that I will discuss are creating impedance circuit or impedance equivalent diagram and basic Ohm's law formula for short circuit calculation. Please, may I have your attention because nakakaantok ito, and let's continue. To start, you need to be familiar with the following electrical components in your single line diagram and how you can convert it to impedance. These are the source utility or power source, the cable interconnections, the transformation of power, the motor loads, and the mixed loads or we call it lump loads. These 5 electrical components determine the total impedance Z of the electrical system in your single line diagram. Okay? To start, here is the point of connection or the source. This is commonly we call the utility, or sometimes it can be a substation or a medium voltage switchgear points of connection or a low voltage switchgear point of connection or a main distribution panel or a given bus. Those are things that can be represented by a utility or a point of connection. Sir, why fault duty is important? Probably you may ask that question. Okay, fault duty is essential in the beginning stages of short circuit calculation because it helps engineers design safe and reliable power system by selecting appropriate equipment to ensure proper protection and coordination and to comply with regulation and standards. Understanding fault duty is crucial for the safety of both the electrical system and the people who work on or near it. Number 1 reason is fault duty starts the calculation of short circuit of a power system. Number 2, fault duty helps you to size the CAIC rating of protection devices like circuit breaker, fuses, or relays. Number 3, fault duty is used to do ratings for equipment. Like a transformer, switchgear, or busbar, we called it to short circuit withstands rating. This ensures that equipment you buy or select can handle stress caused by a short circuit. With fault duty, it makes your calculation reliable because you can rate and specify a protection scheme to isolate faults. You will appreciate that later in this course, okay? Fault duty helps to ensure safety because knowing different fault duty in an electrical system helps you to conduct protection coordination, ensuring safety at all points of all the electrical system. Fault duty is important or useful for system upgrades and expansion. As power systems grow and change, understanding the fault duty at the different location in the electrical system is crucial for proper planning, design, and implementation of system upgrades and expansion. Fault duty is important because we can use it to comply with regulation. Many countries have regulation and standards that require short circuit calculation, including fault duty analysis to ensure safe and reliable power system. Accurate short circuit calculation help meet this regulatory requirement. Okay? Let's go back here. This is the equivalent symbol for impedance utility. You will use it in your creation of your impedance diagram. It composed of a resistance and a reactance, we can call it ZU or utility impedance or point of connection impedance. For the per unit formula, we will use ZPU is equal to MVA base over MVA SC or the fault duty. Then the RPU or the per unit resistance is equal to CPU cosine arctangent X over R, and X per unit is equals to Z per unit sine of arctangent X over R. We can see this formula in action later in this course. Server question: what is MVA base? That's actually a very good question. MVA base is a reference value used in power system analysis when working with per unit calculation. Okay? It represents the base power level for the system. It is typically chosen like number 10 or 100. But mostly 100 is used. Even in ETAP, 100 base is used. Using a common MVA base throughout the system, it simplifies calculation even in manual and software calculation. There was no substantial difference between manual calculation and software calculation. Keep in mind that MVA base must be the same throughout the electrical system being analyzed. If you use 100 as an MVA base, use it to make your voltage supply a base voltage and compute for the base current. Those bases will be used when we go back to the normal value of short circuit. For the per unit formula of the utility of point of connection, we will use what I already mentioned, that CPU is equal to MVA base over MVA SC or the fault duty. Then RPU is equal to CPU cosine arctangent X over R, and XPU is equal to CPU sine arctangent X over R. We can see this formula later. Server question po, ano naman po yung MVA-SC? Okay, MVA-SC or short circuit MVA is a parameter used to get the maximum power that can be generated during a short circuit event in an electrical power system. MVA-SC represents the fault level or the amount of power the system can supply to a fault point during short circuit condition. Ito ang maximum fault that can travel through the point of fault. This is consolidated fault. This is the reason why we need to protect from fault coming upstream from Meralco or other distribution utility, because they require user to protect their system so that their fault will not travel to their distribution line. Kaya minsan nakikita nyo ang bumibigay mga fuse sa poste. That's mean if there is a lightning that hit transmission line, all path to ground will activate first to drain the fault to ground. Then to prevent damages to all connected system, sometimes pole-mounted transformers suffer or sometimes the fuse cut out. MVA-SC is important for power system analysis. It helps us design and determine equipment rating for circuit breaker and other protective devices to ensure safe operation under fault condition. The MVA-SC value is used to determine the maximum fault current that could flow during a short circuit event, which in turn helps to evaluate the impact of the fault on the electrical equipment in residential, commercial, and industrial, which is covered by our topic. Now, the second component in our electrical system is wire or cables. There are lots of it in our schedule of loads, right? So, here is the equivalent symbol to use. ZZ1, resistance and reactance symbol. Remember, in your single line diagram, you need to use your subscript for your impedance. It should be unique. There should be no double entry. When we say ZZ1, that's only one cable in the entire list of cables in the electrical system schedule of loads. Hindi pwede na may ZZ1 ka sa bus 1, meron kang ZZ1 sa bus 2, Then the subscript can be continuous, C1, C2, C3, and so on. Basta wala lang magkatulad, okay? Here's the per unit formula for the cable impedance. It's square root of the square of the resistance of cable 1 plus the square root of reactance of cable 1. The per unit resistance of cable 1 is equal to R from PEC table, closed quantity, length of the wire over 305 times the number of set of the wire per phase kung meron, closed quantity, times open quantity MVA base divided by the KVA base squared, closed quantity. So we have now a per unit value of the resistance. For the reactance of cable 1, it is equal to X from PEC table, closed quantity, length of the wire over 305 times the number of set of wire per phase, closed quantity, times open quantity, MVA base, divided by KVA base to be squared, closed quantity. Please save this in your list of formula, okay? And the impedance is equal to the square root of R squared plus X squared for that specific cable. The next electrical component is the transformer, and we need to convert this transformer into an impedance equivalent. It can be a pole-mounted transformer where you are connected, or a substation transformer or your indoor transformer. For our residential calculation, we need to use the pole-mounted transformer. This is the equivalent symbol of a two circle overlap each other with delta symbol as the primary and Y as the secondary, which is grounded. This is another equivalent symbol we use to our single line diagram, reflecting delta as the primary and Y secondary, grounded. And this is the final symbol we will use for impedance equivalent circuit of a transformer. We can name it ZP1. Always indicate the primary and the secondary with a symbol that you can see in the screen, which is useful during the calculation of zero sequence impedance. Here's the per unit formula for the impedance of transformer. CP1 or CPR is equal to MVA base divided by MVA rating of the transformer, multiplied by the percent impedance. You need to know the impedance of a pole-mounted transformer and its rating. Sometimes it ranges from 0.3 to or 3% to 5%. Okay? And the formula for the per unit reactance is equal to CPR multiplied by sine arctangent X over R, and for the resistance, it is equals to CPR times cosine arctangent X over R. In some manufacturer, there are X over R value given for the transformer. Another electrical component that take the big part of the single line diagram are sometimes the distribution panel that has a mixed load of motors, single phase and three phase, that are below 50 horsepower. As a rule, all motor less than 50 horsepower shall be reflected as lump loads, meaning its kVA should be added and should be represented as one impedance only. Here's the equivalent symbol and impedance diagram equivalent. As you can see, all the cable is neglected due to the rule of parallel wired impedances. We call it lump load motors. In residential, it can be power panel if you have lots of appliances operated by motors. Okay? You may ask, Sir, paano po ang impedance equivalent ng isang panel na combine ang motor, lighting, at convenience outlets? That's a very good question again, kasi kalimitan sa residential electrical system, ganyan ang setup, right? So, sagot. We will answer that in the following slide, okay? Let's proceed. Your lump load can look like this. In a power panel, all was mixed up. There were motors, ACU lighting, convenience outlet, and other loads. What you need to do is, from the schedule of load, get the motor total kVA, and all the static load needs to be neglected. The rule of short circuit contributor shall apply, based from what we have learned from the sources of fault current. Very clear, di ba? Here is the impedance equivalent symbol for the power panel where load are combined. Just I presented a while ago, here's the formula to use for lamp load. The reactance of the lamp load is first computed before the resistance and the impedance. The formula is reactance XLL equals subtransient reactance X double prime D over 100 times open quantity MVA base times 1000 divided by motor kVA rating. Okay? Or motor kVA. That's what's the total motor kVA. While the resistance R is computed as equals to reactance X of lamp load divided by the ratio of X over R. And the total impedance of the circuit for lamp load is Z of lamp load equals square root of R square plus X square. However, you may ask, Sir, what the heck is subtransient D and XR ratio? If you remember, we discussed this in one of the base knowledge of the transient analysis. But don't worry, we will use the rule of thumb. As a rule of thumb, we will use the value of 16.7 for subtransient value. The recommended X double prime D or subtransient is equal to 16.7 or 0.167 per unit as the subtransient impedance for lamp load. It is a rule of thumb oftenly used in power system studies because, particularly when you don't have detailed data on the actual load impedance, this value is used as a conservative estimate to represent the worst-case scenario for fault analysis, especially when evaluating short-circuit current contributed by a lamp load. The reason behind using subtransient impedance 16.7% as a default value stems from the assumptions that the load's short circuit capacity is 6 times the load rated capacity. This assumption helps to account for potential motor contribution during a fault. An induction motor can contribute a significant amount of fault current during a short circuit event. For example, 6 times. Another rule of thumb is we will use XR ratio of 10. You may ask, Sir, why 10? For a lamp load, an XR ratio of 10 is commonly used as a rule of thumb. When detailed information about the actual load impedance is not available, the XR ratio will represent the relationship between the load reactance X and the resistance. The XR ratio is important in power system analysis, particularly for short circuit calculation and fault analysis, as it influences the magnitude of the fault current and the system transient behavior. So we are computing impedance, okay? An XR ratio of 10 is considered to be a reasonable estimate for an aggregated motor load as it captures the inductive behavior of the load of the panel while providing a conservative estimate for fault analysis. Sir Bear, do you have a support reference for that? It is okay to use those values for lamp loads. For further reading, please read the following references. The rule of thumb gives us the nearest amount of fault contributed by a lamp load. Electrical Power System by Z.L. Wada. Power System Analysis by Hadi Sadat. Power System Analysis and Design by J. Duncan, Glover, Mulukotla, S. Sarma, and Thomas Overvay. Electric Power Distribution System Engineering by Turan Gunet. All those books will point the use of subtransient reactance XD is equal to 16.7 and XR is equal to 10. Another electrical component you can find in your single line diagram is the motors larger than 50 horsepower, like fire pump, like refrigeration system. As a rule, every induction and synchronous motor greater than 50 horsepower shall be reflected individually in the single line diagram. Here's the equivalent symbol for your motor 50 horsepower and above. You should reflect its kVA and horsepower rating. Another data you need is the subtransient reactance X"D, and it's not 16.7 anymore. And the XR ratio, it's not 10 anymore. But we will never use it in residential. We will encounter it in commercial and industrial, so please allow me to present it so that I will not repeat it again. Okay? Here's the equivalent impedance diagram. The wire feeding the motor is included, let's say ZZ1, and the motor, let's say ZM1. Observe wire numbering as I mentioned before. It should be continuous and no similar name. Similar to motor numbering, it should be continuous. When you say ZM1, it's the only ZM1 in your entire electrical system. And I hope I made my point very clear. The formula for motor impedance above 50 horsepower is Cm1 equals the square root of the sum of the square of its resistance and the reactance. And for its reactance, the formula is equal to subtransient reactance divided by 100 multiplied by open quantity square of the motor voltage divided by the square of the supply voltage closed quantity. Sometimes those two are similar, sometimes those two are not similar. Okay? Times open quantity MVA base divided by kVA of the motor. For the resistance, it is equal to reactance calculated divided by the XR ratio. If you know the starting power factor of your motor above 50 horsepower, you can find the XR value of your motor using the formula presented in the screen. So, based from IEEE book, most motor starting power factor ranges from 0.15 to 0.3. Higher than that, the motor is running already and its power factor probably ranges from 0.8 to 0.85. Best to use is 0.3 starting power factor. So, the formula for XR is equal to sine of R cosine starting power factor divided by cosine of R cosine of starting power factor. Please save this formula. This will help you later when you encounter 50 horsepower motors and above. You can use the above formula to find the subtransient reactance of the motor using this formula. That is 1 divided by LRA over FLA times the square root of XR squared plus 1, then multiply the result by the XR ratio. LRA can be found in PEC table 4.30. Here our common formula to find the LRA and FLA, but we will not use it in residential, probably in industrial. Server, paano kung lahat ng motor na horsepower were added and more than 50 horsepower ang lumabas? Ito ba ay lump or ito ba ay treated as 50 horsepower above? Very good questions again. Okay, let me answer that. Sagot, kung ito ay lahat ay 50 horsepower below, kahit na ang total ay 100 horsepower, ito ay considered pa rin na lump load. May example dito sa sunod na slide. Take a look. Halimbawa, sa isang MCC or Motor Control Center or panel, may 4 na motor. When added, resulted to 80 horsepower. O, di ba, lampas na yan ng 50 horsepower. But, it is still considered as lump load because there is no motor that is 50 horsepower above. Lahat sila ay below 50 horsepower. I hope you get my point. With all the things that I show, the end result is simplification of impedance. With the simplification of all the electrical components, we can arrive into a very simple impedance diagram where we can use Ohm's law to solve for the short circuit current. The impedance diagram that you saw in the screen is only just a simplification of a complex electrical system, and we will reduce it further to simply find the short circuit on the red bus to an equivalent Thevenin's equivalent circuit. But we will start with residential wiring design before we go to industrial, okay? But as an example, the diagram or the Thevenin's equivalent circuit is the equivalent impedance diagram in reference to bus 2. As you learned from circuit 2, we can solve the short circuit current using Ohm's law in bus 2. More on this later as we go further in our discussion. Just remember that most of the work in short circuit calculation is the determination of the impedance in the point of fault. Then, Ohm's law follows. We are done with the impedance equivalent and its formula per unit. In the next topic, we will discuss the per unit system and why it is used. Let's take a look at the last two items of the base knowledge of short circuit calculation, the per unit and the requirement of short circuit calculation.